People on Zoom that we are recording this, so if you don't want your image to appear, this will be the good time to switch to the video off. So we are very happy to have today Paolo Lipari, who was joining us from remote, and we didn't know he was going to have COVID, so we anticipated that and we asked him to give a seminar from remote. So Paolo obtained his PhD at University of Rome La Sapienza, which is also my alma mater. After 6 years of postdocs, he returned to Rome as a researcher for the INFN, which is the National Institute for Nuclear Research. His main topic of research has been, in general, high-energy astrophysics, with some particular attention to the neutrino physics. He is a prominent figure in the field of cosmic rays. Just to give an example, in 2021, he was awarded during the 37th International Conference of Cosmic Rays the Ocelec Medal. That's an Irish name, so I very likely pronouncing correctly. That is awarded to the distinguished contribution to the cosmic ray physics. Example of previous recipients was Pier Giorgio Picozza, the PI of Pamela experiment, and also Vitaly Ginzburg in 2001. Also was our Nobel Prize. Today, we'll talk us about electrons and positron accelerators. So, Paolo, with that, the floor is yours. Thank you very much.
Okay, really, thanks a lot for this invitation. I'm sorry not to be with you. Okay, so what I will discuss is electron and positron cosmic ray accelerators. Even if I've given a kind of a subtitle to my talk, which is there a positron anomaly, and are positrons accelerated somewhere in the galaxy? And so this is an outline of what I'm planning to talk. So we'll just introduce the spectral cosmic rays, and okay, so this is, I will follow this line, so let me in my first transparency, I'm just showing the shapes of the cosmic rays measured at the Earth. And so note that I have this line is the proton flux. Note that it's divided by 100. And the spectra are plotted, the flux multiplied by a power of the energy, e to the 2.7. So this would be a steeply falling spectrum, e to the 2.7. This is our measurement of electrons plus positrons spectra. These are electrons divided by 1/3. These are positrons. These are antiprotons. And so actually, you should see that the spectrum of cosmic rays is, of course, dominated by protons. Electrons are of the order of 100 times suppressed with respect to electrons, to protons. And they are. It's important to note that it is a steeper spectrum. So here I'm just showing again the same things, and I'm just showing that there is this important feature that the protons are a spectrum of the order of e to the minus 2.7, 2.8. The electrons, so actually here I have measurement of IMS, which are divided into, for charge, electrons and positrons. And these are measurements which sum over electrons and positrons. So when you do not measure the sign of the charge. And so the spectrum of electrons above like 10 GeV or so is a steeper spectrum, e to the minus 3.1. And around 1 GeV, you have a break in the spectrum, which comes steeper. So this line here is a fit to the Hess data, which is e to the minus 4.1. And I think what I found is a very intriguing feature is this fact that the positrons and antiprotons have spectra which are actually not very dissimilar to the proton spectrum. And so they have a slope of approximately e to the minus 2.8, and they are in a nearly constant ratio from, say, 30 or 40 GeV up to several hundred GeV, and the ratio of the two spectra is 2 within error. And so this actually, they appear that these positrons and antiprotons are intimately related. And well, actually, I just wanted to note that these measurements, all these measurements are done by detectors on satellites or balloons. And except for these higher energy points, which are measured at the ground with Cherenkov telescopes. So this allows to extend the measurement of electrons plus positrons up to a region of 10, 20 TeV, separating hadronic shower from electromagnetic showers. So these measurements have been a little bit controversial because they suffer from some sort of systematic errors. So I just wanted to do this remark. So actually, one note is here I'm taking a little bit a more general observation. So here I'm including lower energy data. So these are here, these data below 1 GeV are taken by the Voyager satellite at the boundary of the heliosphere. And so these are measurements on the contrary in the vicinity of the Earth. And so actually you see that the spectra are have different shapes, and so you have this low energy behavior, which is different, and that is high energy behavior where you have these different power laws. And here I've represented this. So actually this says that if you're integrating over the energy, trying to make an estimate of the power density of the spectra, protons are more than one order of magnitude more abundant. So if there are these accelerators, essentially you have two problems that you have to understand. One problem is why the normalizations are so different. And this actually, I think it's understood as an effect of injection of the spectra. And then you have this question of why at higher energy, the spectra have different slopes. And a crucial question, is this an effect that emerges in the sources or it emerges as a propagation effect? And so the point is that the fluxes that you observe, and actually here we are considering fluxes at the Earth, so a single position and essentially a single time. And so these fluxes are generated by sources which are extended throughout the Milky Way and integrating over a long time. And so these are a combination of what the source spectra are and what the propagation are. And so actually interpreting these results, it requires understanding and disentangling source and propagation effects. And you really have, in some sense, three sources of cosmic rays. You have accelerators, those astrophysical objects, or if you want, events like supernova remnant, GRB, and so on, that accelerate particles to relativistic energy. And then you have, in some cases, secondary production. So you have particles which are created already relativistic in interstellar space. And then you have, for many, this is a crucial problem, but I will say actually quite little about this question. But a point is that you could have an additional contribution to these spectral cosmic rays due to dark matter, either self-annihilation or decay. And so actually, so the point is exactly, say, if talking about accelerator, this is a sketch of the galaxy. So you have sources distributed in the galaxy. They inject particle and these particles propagate. And so you're really summing over many sources, many accelerators or many sources. And then you have to understand this propagation in order to interpret the results. And actually here I've talked about what I've shown is and this is important. As you know, the cosmic rays are a very good approximation isotropic. For protons, the dipole contribution to the asymmetry is of the order of 1 per mil in this energy. And then actually, then you lose the results. And actually, the direction of this dipole is not fully understood. It's not clear if this is a flow of the cosmic ray flux or is a contribution from near sources. This is still an open question. For electrons and positrons, where the flux is smaller, the limits of anisotropy are weaker. So currently, the strongest limit come from Fermi-Lat, which is integrates over electrons and positrons. And again, you observe no anisotropy. And the largest anisotropy is of the order of, is more than, cannot be more than a few per mil, or of the order of 1% at the highest energy. So here, I think I'll jump over this, over a few transparency I'm discussing. In order to understand propagation, the standard procedure is to interpret the results of secondary nuclei. So here you have measurement of a primary nuclei, which are proton, helium, carbon, and oxygen. And you have that the secondary nuclei, like boron, lithium, beryllium, and boron, are steeper. So the assumption is that these spectra are created by the fragmentation of primary cosmic rays, and that this the ratio between primary to secondary is an illustration of the fact of how much material the primary cosmic rays have crossed. And so from this ratio, you can find out what is the column density that the primary cosmic rays have crossed, and what is their energy dependence. For example, you see that, say, lithium is generated in this way, and a series of works in the past have demonstrated that the column density that is required to generate the secondary nuclei is of the order of 10 grams at a few GeV, and then is decreasing like a power of rho here is rigidity, and falls as rigidity. And so this actually can be interpreted as a measurement of the lifetime, of the residence time of particles. But this is the translation from a column density to a time requires to assume that the column density is integrated traveling through interstellar space. And so actually this is a crucial problem. Is this column density integrated in the vicinity, I mean, in a general travel in interstellar space, or in the vicinity of the sources? If this is interstellar space, then you can translate this at an energy of the order of 10 GeV. The residence time of cosmic rays is of the order of 100 million years. So this actually has immediately consequences for the electron and positron propagation. Because if for protons and nuclei, energy losses are negligible during a residence time of this order, this is not the case for electrons and positrons, which suffer energy losses for synchrotron and inverse Compton scattering on the radiation fields which are present in interstellar space. And so actually, you see that this is the kind of characteristic loss time for electrons and positrons in the galaxy. And so actually, you see that essentially when the energy increases, the loss time decreases more rapidly than the escape time. And so at a certain point, electrons and positrons will be dominated by energy losses. And the assumption is the most commonly accepted result is that this is happens at an energy of few GeV, and so that the spectrum of electrons and positrons is shaped by energy losses from a few GeV. And you see that if for positrons, the standard mechanism of production is secondary production. So the dominant process will be, essentially the production of positive pions that then change decay to electrons. And this actually, if this is the mechanisms, you know what is the shape of the injection spectrum. And the injection spectrum is essentially parallel to the proton spectrum, and And so the fact that you find, the point is that this would imply a spectrum which is much softer than what is observed. And so this is interpreted, this is the so-called positron anomaly. And this implies that you must have an additional source which is significantly harder than what you're observing. So the remark that I'm making here, that our alternative possibility is that the residence time of positrons in the galaxy is in fact much shorter, and energy losses are negligible. And therefore, the propagation of positrons and antiprotons is essentially approximately equal up to an energy of the order of 1 TeV. And so discriminating between these two possibilities is a crucial problem for understanding the existence or non-existence of essentially positron and electron accelerators. So here I'm illustrating this.
Oh, Paolo, excuse me, 5 minutes.
Oh, thank you. Okay, so anyway, this is what I'm showing. So the question is at what energy the energy losses become dominant. Actually, as you see, this is again, I'm showing the same spectra, and the question is, if to understand, you see, you have this softening, this break, both in the electron positron spectrum and in the positron spectra. And so the question is, what is the critical energy? What energy losses become dominant? And so to discriminate if these energy losses is at the order of 1 TeV or is at the order of a few GeV. And so this is the question that you want to understand. And okay, so I would have a discussion about gamma rays. And so actually for gamma rays, you have a lot of strong constraints on dark matter results. Well, anyway, so this is the catalog of the Fermi sources. And actually, it's interesting that the Fermi sources have a significant contribution from pulsars and pulsars with nebula, and also from supernova remnants. And the same things is at TeV energies. So you have an important contribution of pulsars and pulsar wind nebula. And so actually here I'm consuming my time very quickly. So I wanted to make a few comments about supernovas as the status of understanding of the supernova paradigm as main accelerator of cosmic rays. But anyway, the point I want to make is, I think there is solid evidence that pulsars are accelerating pairs of electrons and positrons. Already a discussion of the Crab Nebula is clearly shows that you have that from the pulsars you're accelerating a population of electrons or electrons and positrons. Here is this and these things accelerate and generate this a nebula which self-confine these relativistic particles. This is a description of the Crab Nebula, and you see there is clear evidence that the emission from the nebula is generated by a population of relativistic, well, say electrons and positrons that contains a large energy in relativistic particles, and these relativistic particles emit synchrotron, and then they re-emit a higher energy, emitting inverse Compton scattering on these radiation fields, and these things is consolidated, but this population of electrons and positrons remained confined in the nebula, and so the question is again to try to understand how this population of electrons and positrons can be released from the pulsar wind nebula and enter interstellar space. And recently, there's been a measurement about the escape of electrons and positrons from these objects. And there have been these Hawke results that demonstrate that you have particles which are leaking out of these pulsars with nebula. And okay, so the point that this would require a critical discussion. The point I want to make it is, I think there is solid evidence that pulsar and pulsar with nebula are accelerator of positrons and electrons. But if this contribution is sufficient to become the dominant contribution to the spectra of electrons and positrons remains an open question. And the last part of, I think my time is finished now. I wanted to discuss how you could solve this ambiguity. And I think there are some observations that could do this. One, of course, is to do more studies of pulsars with nebula. And there are other things which I'll just mention. A key factor is to measure anisotropy and spectral distortion of the cosmic ray electron and positron spectra. And then there are to measure other probes of cosmic ray propagation. So this is, at a certain point, the granular nation, the discreteness of the cosmic ray sources should emerge. And so just to say, it's kind of clear, when you go to higher energy, you are starting to select sources which are younger and closer. For protons that live longer, you would have probably hundreds of sources contributing at 1 PeV. But in the standard propagation model, you should have just a few sources contributing at an energy of 1 TeV. And okay, so you should have a picture of this sort. So I think a key observation is try to observe anisotropy and spectral distortion at the high end of the electron and positron spectra. And I think this is a crucial observation. So this is my remark. I think anisotropy and spectral features should appear soon if you don't want to revise profoundly propagation models. And well, I had another 2 examples, but I think I'll skip them, which are beryllium can be a measurement of propagation, and also and there are new data which people are expecting that could be very relevant. I'll skip on some conservation antiprotons, and these are very schematically my conclusion. So the first point is, I think this is a very important question. The question is, the positron flux is dominated by a contribution of a source and not by secondary production. And so this remains a very important question, which I think is of central importance for cosmic ray physics. And I think we are now understanding that pulsars and pulsars with nebula are accelerators of electrons and positrons, and we are understanding many things, but many things remain still not well understood, and is unclear what is the contribution of the population of relativistic electrons and positrons that are observed in the vicinity of the Earth. And I think there are a number of observations that should clarify this question, hopefully in a time reasonably short. Okay, I hope I was not too obscure, and thank you a lot. Thanks a lot for your attention.
Thank you so much. Okay, let's start with questions. Do we have any questions from the online people? I don't see any. Do we have any questions from the room? Well, you think question about the constraint on the propagation. So at these higher energies, beyond hundreds, beyond tens of GeV, what is your feeling about the role of the different contributions, different types of the contribution of different types of turbulence? If you compare, for example, the fast mode pre-existing turbulence with the one which is self-excited by the cosmic rays. So recently there has been some work suggesting that they are both necessary in order to explain for example, the Voyager data.
Well, I think this is a very interesting question. I have a little bit of critical, many studies are leaving the properties of turbulence as essentially a free parameter. So you fit the rigidity dependent of the diffusion coefficient. And I think this is unsatisfactory. And so you should, I think you have a lot of work to do about the space and rigidity dependent of the diffusion coefficient. And I think you have a question about the rigidity dependence and how turbulence can be different in a different distance from the galactic plane, for example. So I think I think you should probably, I think when a full understanding will be obtained, you will discover that propagation is significantly more complex than what current models, how is described in current models.
Mm-hmm. Yeah, all right, thanks. Any more questions from the audience here? I cannot see any. Okay, let's thank Paolo again. Thank you so much, Paolo.
Thanks a lot. And yeah, if anybody wants to discuss with me, I would be more than happy to do it in other. And thanks again for the invitation. I'll stop sharing the screen now.
Thank you. What is your microphone? Oh. Wow. There is no. There is no other microphone. Sorry. I give them thoughts. To work now.
All right, well, while you guys figure that out. All right, so I'll introduce our next speaker while they're troubleshooting the microphone. So next up, we have Christopher Moore. So Chris received his PhD in 2017 from the University of Colorado and was an International Astronomical Union PhD prize winner. His dissertation research included NASA Space Technology Research Fellowship project to help create high reflective UV visible IR coatings for the next generation of astronomical space telescopes. And he did this work under Professor Kevin France. Also in his PhD work, he worked on detector characterization and solar science analysis of the miniature X-ray solar spectrometer CubeSat mission. And he did this work under Tom Wood. He's currently working here at the CFA, as I'm sure many of you know. He's holding a dual appointment here at SAO and HCO. His current science research focuses on solar corona, specifically working on techniques to improve constraints on the plasma temperature distribution, elemental abundances, and deriving connections between magnetic and radiative fluxes. Chris utilizes X-ray and EUV observations, compares them to models, and works to develop new instrumentation for better measurements. His current instrumentation research includes working to develop new soft-ray X-ray spectrometers for future sounding rockets, CubeSats, small sats, and large satellite missions. So with that, go ahead and take it away, Chris.
Can everyone hear me? Yeah, we're good. Thank you, Amy, for that comprehensive introduction. You didn't have to read off everything, but I appreciate it. So this talk will be a little bit different than the previous talk, which was highly focused on the science. This will be more of a programmatic, logistical, from concept to initiation of a project type of presentation. And this talk will be on the SWIFT Solar Activity X-ray Imager sounding rocket opportunity called SSAXI. Again, as mentioned before, my name is Chris Moore. I'm definitely not the only person to contribute to the SSAXI opportunity. There are numerous individuals here. This is a non-exhaustive list. And if I were to thank everyone by name, we'd be sitting here for the whole talk. So we'll get straight into it. So before we talk about the SSAXI-Rocket opportunity, we need to talk about the SSAXI small sat opportunity, which preceded it. And so we're mostly focused on the solar corona via soft X-rays, as we can see here, as a function of time from the Hinode X-ray telescope, which creates spectrally resolved images, spectrally integrated images, but spatially resolved. We can see it was a function of time that there's a very large difference in the emission, non-homogeneous, anisotropic, and there are strong concentrations of magnetic field, which confine hot plasma above 2 megakelvin, which radiates cool via radiation. And these are what we call the active regions. But what we see on this other portion of the sun at 2008, which we call the solar minimum, where there are not many active regions present, which are driven by the magnetic field concentrations, that it seems to be almost ubiquitous. Almost, there's this diffusive emission that we see that pervades around 1 to 2 megakelvin. Most of the information and studies that you hear about are focusing on active regions and flares, like what are the heating mechanisms, what gets the plasma above 2 megakelvin. But not as much research has been done in terms of consistently measuring this quiescence, always pervasive, diffuse emission. And that's one of the things that we are motivated in investigating. As you see here, if you were to look, the dynamic range of Hinode X-ray telescope is fairly limited. So when these bright active regions are present, it's very difficult to have the same dynamic range, to have the same sensitivity to see this dimmer coronal emission. And that's what SSAXI small sat is designed to accomplish. We already have seen that spatially separated, spectrally integrated images provide a wealth of information and knowledge, but there is much more information that can be uncovered if you can create spectral images. Here on the right are synthetic spectra that I've created as a function of isothermal plasma temperature. Temperature is increasing vertically here, and in the video will loop, so you'll see this again. This is calculated using the optical thin approximation from the radius of loss function on the left, which is highly dependent upon free emission, free bound emission, and bound transitions from iron, magnesium, silicon, sulfur, oxygen, etc. For the 1 megakelvin plasma, as you see here, the slope is very large, where the intensity falls off drastically as we go to higher energies. That's the intensity contrast that we need to be able to detect with our future observatory, the 1 megakelvin plasma. As you see, as temperatures get hotter, around 10 megakelvin or greater, there's less of a difference in terms of the intensity near 1 keV and 10 keV, which are the most of the flare and active region observations. So that's our dynamic range challenge, spectrally, spatially, and temporally. So solar X-rays, they yield abundance of information on the temperature, density, magnetic field structure, velocity, if you can get spectral measurements at high spatial spectral resolution. And so what we want to investigate for the quiescent sun, or the quiet sun active regions and microflaring heating mechanisms different. And when I say quiescent sun, I mean not a lot of large transients, large solar flares occurring. So this is a question that's very difficult to answer, partly due to the limitations of our observatories. Hence, we enter SSAXI small sat. And since this is focused on SSAXI-Rocket, I will not spend much time about SSAXI small sat. Hopefully in a few years, I can come back and give a presentation talking all about SSAXI small sat in glorious detail. But for right now, the main objectives are to conduct continuous full sun, spatially resolved soft X-ray measurements for a statistical study of transient events, active region evolution, quiet sun variations. Part of this region for micro flares, or these small transients compared to large flares, is to get a bridge between previous observations that have more sensitivity to these larger events, but there's a discrepancy. So we have UV measurements here and some X-ray measurements here. And then we have X-ray measurements, hard X-ray measurements mostly here and soft X-ray measurements. But there's, as you see, there's a difference, a spread here where we are missing wealth of information. And so SSAXI is designed for the bridge between these thermal energy events and the frequency of these events. That leads to direct energy input to, can these small transient events deposit enough energy to actually heat the solar corona during these quiescent times? that's essentially the big question, the big main goal. So for SSAXI small set, we have a series of instrument parameters, and we have forward modeled and synthesized what the observations would look like, and that's on the left here for a full sun image integrated over about an hour. We can do shorter times than that, but this is just for example. And what we see for the blue, red, and green dots, they're showing the spatial spectra that we can obtain. Current observations, if they're spectrally resolved, they're mostly spatially integrated. And as I showed you with XRT, if they're spatially resolved, they're spectrally integrated. We're just trying to do the combination to address this fundamental question here. Kathy Reeves has contributed immensely to formulating some of the science questions in detail, which again, I'm just giving you the high level discussion here. So this is where we want to go. These are the observations we desire to make. As of right now, they are a fantasy. They're in our dreams. We dream about it every night, right? As scientists, this is where we want to go. But the question then is, how do we get there? So in general, since we don't have the technology readily available to just procure, assemble, launch on a satellite, a small satellite, we have to actually go through that process ourselves. And this is an example of mission development. It's non-exhaustive, but essentially, do we have the technology? If so, is it ready to integrate into an instrument? Can it meet the, when we just assemble it into an instrument, what are the capabilities, and can those capabilities address and meet this performance requirements? And do these performance requirements satisfy the science requirements, and et cetera? Does this allow us to provide closure on our science questions, our science goals? This is one way of having the flow traditionally, and the best way to go about it is the way that I've shown here on the right, where you set main questions, which we actually did with SSAXI small set. This drives the performance requirements, instrument capabilities, and then is the technology ready? So that's what we did for small set. But to get to the rocket, we went this way. So we were this set our technology that we needed, and then we go back this way. So how do we get money to actually execute what we need to happen with the instrumentation? So we need to develop the technology first. In our situation, we have a focusing optics telescope. So we need to develop the optics to the level we can launch them, the detector and camera system, and then also the data processing algorithms. So we know where we want to go in the grand scheme of things. We know what we need to do to get there. In the meantime, now we need to procure the funding to actually make this happen. So some of the funding sources that we've obtained are internal research and development programs. We've also procured external funding from NASA for the development of our camera system and our sensor. And we also have an opportunity to spaceflight verify these components as an instrument on a ride along to a sounding rocket in 2024. And we obtained that funding through NASA low-cost access to space. So thank you, NASA. We appreciate it. So again, on the right, we have developed this design of multiple X-ray telescopes to get the dynamic range, the spectral coverage, the performance requirements. This is in 2028 for the next solar minimum. That's our goal. To get there, we have to have some type of intermediate technology development, and that is SSAXI-Rocket. We will be launching as a ride along to the high C flare payload, which I'll discuss a little bit more further along in 2024, which is funded. So we'll take these X-ray imaging sensors, take a version of them, modify them that's compatible to the rocket mission, and launch it. And we are also developing the future generation of engineers and scientists. An example of ours right here, Sofia Sanchez-Mayas, PhD student here at the CFA. She's working as deputy PI, assisting us in this. And her imprint is all over this project, even though you will no longer see her face explicitly mentioned. So we have funding, we know where we want to go. How do we convince the community that this is worthwhile pursuing in the long term? Is there some critical limitation in the current performance of the instrumentations of observatories in space for our particular scenario? Yes, there is. Current CCDs saturate and bloom. So essentially for during large solar flares and extreme ultraviolets. So what you see on the left is the Solar Dynamics Observatory Atmospheric Imaging Assembly. During the larger flares, we see that there's a bunch of white here, which is basically the charge filling up the well in CCD. So we can no longer get more information, and then it's blooming over to adjacent pixels, destroying this whole region, which is the money shot. This is what we really want to investigate in terms of flares. So we need to get around this. And in the X-rays, it's even worse, as you can see here. I don't even have to say anything, right? We just lose all of our information for that time frame. So we are implementing newer sensors that have in their architecture a way of mitigating the blooming and mitigating the saturation. Another additional attribute to these sensors are that they read out very, very, very fast. So we can look at high time cadence phenomena. Here's an example of the observation timescales on the horizontal axis for spatially resolved instruments. Our proposed SSAXI-Rocket is 2 orders of magnitude higher timescales than Hanode X-ray telescope, which I showed you on the right on the previous slide, in the X-rays in the EUV AIA. Now, the highest time cadence observations currently are spectrally integrated and spatially integrated, and those are these up here. We are still roughly an order of magnitude faster. These are our design parameters. The question is, can we make that happen and achieve on this NASA sounding rocket opportunity? All right, so we have funding. We've pointed out a critical need in terms of performance across the board. This is more than just SSAXI-Rocket, SSAXI small sat. Other observatories can use these sensors. What about the science case? What is interesting to the scientific community that they would like to see addressed in this short rocket flight? Since we have these high time cadence observations, something that we still don't have closure on are quasi-periodic pulsations in large solar flares. They occur, we observe them across the entire electromagnetic spectrum, from radio down to hard X-rays. Laura Hayes is a collaborator on our project. She's worked on her PhD on quasi-periodic pulsations. And these QPPs in amplitude can be 1% or less. And it's important to detrend the light curves. So here is an example of the soft X-ray, spectrally integrated, goes for shorts that you'll hear me mention over and over. When you detrend them, you can see that there's these oscillations, and they vary actually as a function of the flare. And so there's belief that this is an important constraint on the energy release process in solar flares. What's driving them? Is it intermittent particle acceleration? Are these trapped particles mirroring back and forth and radiating? Is it just the magnetic field itself oscillating, providing density perturbations, leading to changes in the radiative loss locally? We don't know. As I said before, they vary in amplitude during the flare, and pulsive and decay phases are very different. For our rocket opportunity, which is roughly 5 minutes of observations, we'll mostly be observing the gradual phase, the thermalization process of the flare, where most of the soft X-ray and EUV emission occurs. On the left, here is AIA again, and we see that saturation occurs. So we can't even analyze this spatial region for the QPPs. So this is what SSAXI-Rocket is designed to address. Can we see the spatial distribution of QPPs and how they vary? So more to the actual hardware. Dave Caldwell is our mechanical engineer. He doubles as our project manager. He helped us design our optic bench, thermal constraints, structural constraints. So here we have our SSAXI X-ray telescope, a grazing incidence telescope, which focuses the X-rays down through filters and onto our high-speed readout sensor. SSAXI instrument will be implemented on the high-C, high-resolution coronal imager. It's an EUV imager that's focused on 10 megakelvin plasma. And so we sit here, we ride along, so we don't have to do all the work for the rocket, just our instrument. So a quicker turnaround. And so the other component that I mentioned before earlier, the optics. So there are many people that have contributed. Some are in this room. Jay Sub Hong, Ricardo Bruni, Suzanne Romain have led the optic development. We're replicating shells off of our mandrel, which are fairly smaller size, 1 meter focal length. These optics have recently been tested at Marshall Space Flight Center. The PSF is shown here. We are achieving roughly 4.8 arc second forward half maximum and 15.8 arc second half power diameter, which is good. So it's a good step in the right direction. And here are some of the critical individuals, again, non-exhaustive, that have contributed to the development of these X-ray optics for SSAXI-Rocket. Now our detectors, our sensors, they have been procured by SRI. We are modifying the camera packaging that they're delivering and providing additional packaging and controls on the back end. Right now, we have individuals working on as a team to bring up to speed our X-ray calibration facility so that when the sensors arrive in a month or two, we can go calibrate them and integrate them to our instrument for delivery. So we're using CMOS, this X-ray sensors. So direct detection of X-rays and reading out very fast, at least 10 hertz. And one of the advantages of CMOS, not just for this opportunity, but in the future, which people know about, especially for links, their radiation tolerance is typically better than CCDs. They can operate for similar noise characteristics at higher temperatures. And they have a wide dynamic range, which is excellent for our soft X-ray solar flares, which has huge changes in their intensity. These are some of the individuals that have been working meticulously over the past few months to get our CMOS sensors up to speed and and to bring up to speed our calibration chamber. So when we combine our detectors with our optics, with our filters, these are the general performance parameters that we've set forth. 1 meter focal length, 20 arc minute field of view with a roughly 9 arc second forward path maximum spatial resolution as the requirement. And as you saw, we're getting roughly half that with our current optics. That's a good thing. We have our spectral energy range, and as a trade-off, I showed you spectral images is where we want to go, but a trade-off for this rocket opportunity is to focus on the intensity contrast and the time fluctuations of the quasi-periodic pulsations. So we're going to integrate across this entire spectral range, just for the rocket though. Our dynamic range is pretty good, 10 to the 5. So we're content with that. On the left is a plot of our sensitivity as a function of photon energy. And we have peak sensitivity around 1 to 6 keV, and it falls off drastically as we go to 8 and 9 and 10 keV. This is primarily due to the reflectivity of the optics and the quantum efficiency of our sensor. If one were to take this and translate it to a temperature, plasma temperature sensitivity, we have a peak sensitivity around 10 megakelvin, which is in line with the high-C payload. Remember, their primary objective is to look at the 10 megakelvin plasma in extreme ultraviolet, and we were looking at that similarly in the X-rays. So there's nice synergy there. When do we saturate? So here is a model of essentially what we envision when we would saturate. And it doesn't even happen until we get to fairly large intensities in the GOES X-ray calibration. So this is a nonlinear response when you get to higher energies for GOES, so we don't fully know. And that's another thing that we can contribute. Our response is more linear than these sensors that are typically used for soft X-ray flares. But this corresponds roughly to about a 5x5 flare or larger. Don't necessarily worry so much about the class name. It's more of the watts per meter squared that's relevant. But we shouldn't saturate unless there's a huge flare. But we'll see. This is what we do it for, right? Now, in terms of some of the science, Jeffrey Reif is a colleague working with us from the Naval Research Laboratory. He works on models that take magnetic field reconnections, energy inputs into hydrodynamic models for the coronal plasma and sees how they respond. Temperature, density, velocity, ionization states, radiative loss, et cetera. Flows also into the corona from the chromosphere. So in some of the models that he's already created for us, we have as a function of time, the GOES integrated soft X-ray flux as a function of time, and his models of multi-threaded loops that are being injected with energy and then using his hydrodynamic models to model the response. The collection of these loops, which are these blue dashed lines, create this thicker blue line, which matches GOES fairly well. So his model has pretty good fidelity. And in the bottom row, we synthesize what SSAXI-Rocket should observe for the duration of a flare. And again, we're only observing 5 to 10 minutes, so it'll be some time frame in the middle here. But it's good to see that with our spatial resolution, we should be able to see differences in the foot point and the higher loop tops. Again, GOES doesn't even have spatial imaging, so this information we don't even have right now. So in theory, this rocket could turn into a satellite that has this particular spectrally integrated high time cadence observation techniques, not just the spectral images that I mentioned before. So what's our schedule? I won't bore you with all the details, so this is a simplified schedule. You can add 2 months to the start time because we received our funds from NASA 2 months later. But essentially, as you saw, the optics are almost ready to go. There's further testing happening over the next few weeks at Marshall Space Flight Center. Our detectors are arriving in the next month or two. We have cameras, boards arriving. They're being tested and developed right now. We'll integrate everything in the next few months. And in the summertime, we'll be delivering to the main payload, which will be shipped down to Marshall Space Flight Center for further testing. And then we go to White Sands Missile Range for vibration testing, balance, center of mass testing, et cetera. And then we eventually go to Alaska. And so HI-C plus FOXY, which is a hard X-ray imager plus SNFs, which is a EUV spectrometer. 3 sounding rocket payloads will sit at the missile range in Alaska. We will sit there literally for a month and wait day after day after day till a large flare happens, and then we trigger the rockets sequentially to observe, not simultaneously, but fairly close in time. It's called the Flare Campaign in March, April 2024. So we have 1 more year. So hopefully next summer I can come back and tell you guys how our observations went, how things went with the whole Flare Campaign. We're also having this aligned with Solar Parker and the Solar Orbiter. So it's a pretty big opportunity that hasn't happened in recent years. So I want to thank everyone for your time listening to me talk about SSAXI-Rocket and some of the process we went through to get it to this stage, and eventually what we like to see for SSAXI smallsat. All right, now I'm open for any questions, and thank you for your time.
All right, any questions from the audience? Yep.
Yeah, so what is your launch trigger condition? Is it specific flare class that you're trying to target, or how do you say go more specifically?
Our trigger is goals C5 or greater, and essentially we're going to monitor the goals light curves, and so there'll be a delay, of course. And there's a 15-minute T-minus 15-minute hold. So we go through all the procedures, and when that happens, when we get to the state of T-minus 15, we literally just hold and wait. So we can't do this every single day. There's a day off after, so we sit for 1 day, and you have to have a day off, and the next day you can try again, because the staff, the whole team gets tired. I mean, it'll be 30, 40 people working hands on deck every time we get ready to go launch.
That's a question online. Someone just said a great job. So along those lines, why can't you launch them at the same time for a simultaneous measurement? Is it just like the logistics of the launch site?
Yeah, for safety purposes and the logistics of the launch site. As of right now, we're not the military, so we can't just launch them simultaneously.
Okay.
And we have to go to Alaska instead of White Sands Missile Range, basically because there's a major highway that goes through the missile range in White Sands in New Mexico. And so for safety purposes, we can't close off the highway for the whole day, just for a few hours.
Oh,
I was wondering what the field of view of these telescopes are supposed to be. They're going to have a full disc of the sun in each one, or you have multiple? Okay, there you go.
So this one's 20 arc minutes. The sun's about 30 arc minutes.
Okay.
So we won't have a full field of view for this. There was a compromise. For SSAXI smallsat, we will. It's 40 arc minutes is our goal for SSAXI smallsat. And I actually have another slide. These are older requirements that we set for SSAXI smallsat. Field of view of 40 arc minutes.
So there's a small chance you might miss the flare in your launch.
There's always a chance you can miss a flare. The bore site or the center of the field of view with optic axis of SSAXI-Rocket is designed, and we're going to make sure that it's co-aligned, or the bore sites are aligned with high C flare. And high C flare has a smaller field of view than SSAXI-Rocket. So if we do that, and high C flare points at the flare, then we should be good. But you never know, things can get jostled out of place with the vibrations on the launch. The sounding rockets are fairly small compared to like large rockets for satellites. So it's pretty violent. But there's a bunch of safeguards we put in place to try to make sure that it does not happen. And that's partly the vibration testing that we do at White Sands. We see if we put in a bunch of frequencies and like powers at different frequencies and see if does that perturb anything out of line.
For the satellite, you had 6 telescopes, are those different wavelength ranges?
Yes, they are. Different wavelength and different intensity sensitivities.
I was just wondering about the telemetry from a sounding rocket. Do you actually send the data down, or is it just recorded and then you cover it?
Traditionally, both happen, and for high C and another instrument on the high C payload, their telemetry down and is stored on board. This opportunity, the way it's worked out, we have to store everything on board. And so we won't have anything telemetry down directly for this launch. But we're a ride along, we're not the main thing.
Just wonder if you do get a very bright X-class flare, so you're saturated, do you just lose sort of the streak at the core of the PSF in some region, and you can still get useful information from the wings of the PSF? Or do you hit other kinds of problems in such a case?
One can still back out some useful information from the wings of the PSF. For us, the saturation, if it were to occur, it would be a problem, but it would not, there's no anticipation that blooming would occur. So it would still be localized. And if you remember the image the video that I showed with Hanode X-ray telescope, the blooming can be severe.
Yeah. Thank you.
No problem.
Any additional questions? I don't see anything online. So with that, we'll thank Chris again.
Sorry, there was another microphone.